The bridge that shook itself to death. Welcome back to Blueprint to Reality, the channel where invisible forces, design decisions, and engineering failures are brought into the open. Bridges are designed to carry enormous loads. They resist gravity, traffic, wind, and time itself. But what happens when a bridge doesn't break under weight, and instead destroys itself through motion? Today's video explores one of the most haunting engineering questions. How can a bridge shake itself to death? Introduction. Some structural failures happen in an instant. Others unfold slowly, through repeated movement, vibration, and fatigue. When a bridge begins to vibrate, energy builds, stress accumulates, damage grows invisibly. Eventually the structure fails, not from overload but from self-induced motion. In this video we'll examine why bridges vibrate, how small movements become deadly, the engineering mistakes behind vibration-based failures, real bridges that shook themselves apart, and how modern engineering prevents this today. 1. Why bridges move in the first place. Bridges are not rigid objects. They are designed to flex under load, expand and contract with temperature, respond to wind and traffic. This flexibility is intentional, but it must be controlled. Sources of vibration. Wind gusts, traffic, loading, pedestrian movement, seismic micromotions. If vibration energy is not dissipated, it accumulates. 2. The dangerous concept of resonance. Resonance occurs when external forces match a structure's natural frequency. Vibrations amplify instead of fading. A small repeated force can cause large oscillations, fatigue, damage, connection failures. Resonance is silent at first, until it becomes unstoppable. 3. Aeroelastic effects. When wind becomes the enemy. Wind doesn't just push bridges, it interacts with them. Vortex shedding. Alternating vortices form behind bridge decks. These create rhythmic lateral forces. Flutter. Wind feeds energy into motion, oscillations grow exponentially. This is how a bridge can be destroyed without extreme wind speeds. 4. Real bridges that shook themselves apart. Tacoma Narrows Bridge collapsed due to aeroelastic flutter, demonstrated torsional vibration failure. Millennium Bridge, London, swayed due to pedestrian-induced resonance, required retrofitted dampers. Angers Bridge, France, collapsed under synchronized wind and foot traffic, demonstrated human-structure interaction. These bridges didn't fail from weight. They failed from uncontrolled motion. 5. How vibration causes structural death. Repeated motion causes fatigue, cracking, bolt loosening, weld failure, cable stress accumulation. Over time, structural stiffness decreases, natural frequencies shift, vibrations worsen. The bridge enters a feedback loop of failure. 6. Engineering mistakes that allow self-destruction. Common errors include ignoring dynamic analysis, over slender designs, poor aerodynamic profiling, lack of damping systems, underestimating fatigue. These mistakes don't cause immediate collapse. They plant the seeds of long-term failure. 7. How modern engineering stops bridges from shaking apart. Dynamic analysis. Engineers calculate natural frequencies, mode, shapes, damping ratios. Aerodynamic design. Streamlined decks, wind fairings, vent openings. Damping systems. Tuned mass dampers, viscous dampers, cable crossties. Monitoring systems. Sensors detect vibration and fatigue, early warnings prevent disaster. Lessons for engineers and students. This type of failure teaches us motion is as dangerous as force. Fatigue is silent but deadly. Dynamic behavior cannot be ignored. Safety depends on energy control. Engineering is not just about strength. It's about stability over time. Conclusion. The bridge that shook itself to death was not weak. It was misunderstood. It moved the way physics demanded, and failed the way engineering allowed. Modern bridges stand today because engineers learned to listen to motion before motion turned into collapse. If this video changed how you think about bridge vibration, Like, share, and subscribe to Blueprint to Reality. Comment below. Which structure should we analyze next? A tower, a dam, or a stadium? At Blueprint to Reality, we don't just build structures, we understand how they move. See you in the next video. Bridge at night, triangular ruler.